All right, hello everyone. Welcome to the next part of this lecture. In the previous part, we derived the equations for the underdamped natural response of a parallel RLC circuit, and in this part of the lecture, we're going to do a circuit problem. All right, so very quickly, let me do a 1 minute recap. This is what's needed to solve any circuit, parallel RLC circuit, and to find the response, underdamped response, right? So again, most of the steps are very similar and repeatable in between responses, and usually for circuit solving. So I'm gonna do a kind of a brief recap here. Again, the first step is always finding the initial conditions, right? Whether you have a first order, second order circuit, or whichever the response we are talking about, even the natural or the step responses, right? So the first thing is we find out the initial conditions. In this second order parallel RLC circuit, we have to find two initial conditions, the V naught and the I naught. And if that is given in the question, great. If not, find it by solving the circuit at t equals less than 0. The second step, of course, if RLC and values are given, then find the values of alpha and omega naught. And then based on these values, you figure it out which response it is, right? In this particular case, we are talking about an underdamped response. So in the case of underdamped response, your alpha square should be less than omega naught square. Then you can potentially use this equation to solve the to get the voltage response of a parallel RLC circuit. There are three unknowns in that equation. One is omega d. Here's an equation for the omega d. The other one is the b1 and b2. We know the value of the b1 that we derived, and we know and by replacing the value of the b1 over here, and I naught and v naught, you can find out the value of the b2 as well. So it's literally finding out the initial conditions, figuring out which response it is, and then taking the right equation and filling out the constants. So we're going to do this exercise here. Okay. So let's look at the circuit now. Here's a parallel RLC circuit where initially there was some DC source that charged the capacitor, provided energy to the capacitor and inductor. And then it was at time t is equal to 0, it was kicked out. And of course, now the energy will be released in the circuit via a resistor, so the energy gets dissipated there over time. So that is why it is the natural response, right, of a parallel RLC circuit. We have the values of the capacitance, inductance, and resistance given already. Interestingly, the problem already gave us the value of the V naught, and also the initial voltage across the capacitor is V naught, and the value of the inductor as I naught. The initial voltage across the capacitor is V naught. You can assume that there was a way where the initial DC source was connected in such a way that it was only charging or it was only storing the energy in the inductor and not the capacitor. That is why V naught is equal to 0. Okay, and what we are interested in finding the voltage response equation for t is greater than 0, and then we are also interested in plotting that V of t for this time duration. All right, so let's get started. In order to solve this, the very first thing is, again, as I mentioned in the step number 1, what do? We find the initial conditions. The initial conditions are already given to us. V naught is 0 volts and I naught is minus 12.25 milliamperes. Okay, so this is great. Then step number 2 is we find the values of, since the value of the R, 20 kiloohms is given, right? We know R is 20 kiloohms, capacitance is 125 nanofarads, and inductance is 8 Henry. We have to find the values of alpha and omega naught or omega naught square. Okay, so let's find the value of the alpha. Alpha is equals to 1 over 2 times RC, 1 over 2 times 20 kilo times 125 10 to the minus 9. Alpha comes out to be 200 radian per second, right? Now let's find the value of omega naught square. Omega naught square is 1 over LC, or omega naught is 1 over square root of LC, right? So we get 1 over L, inductance is 8 times 125 nanofarads. It came out to be 10 to the power 6 radian per second. Once we find the value of the alpha and omega naught, the step number 3 is we practically compare these values, which one is greater or less, and then determine the response. Okay, so I can easily see that my omega naught is greater than alpha, right? my omega naught is greater than alpha, right? Why? Because 10 to the 3 is greater than 200. So, of course, my omega naught square should be greater than alpha square as well over here. So, this must be underdamped response. If this is an underdamped response, great, because we have already derived the equation for the response. V of t should be equals to b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt for t is greater or equals to 0. Okay, so this is the equation, and we need to find the three values, omega d, right? In order to solve this, I need to find the value of omega d, b1, and b2. Right, so in step number 4, I find the value of omega d. Right, so this is a radian damp frequency. Okay, so omega d equals, if you remember, was equals to omega naught square minus alpha square. Right, so I can do 10 to the 10 to the 6, omega naught square is 10 to the 6 over here, minus alpha 200 square. Omega d should come out to be 979.8 radian per second. Okay, so this is nice. We ended up finding this as well. Now step number 5, I have to find the values of b1 and b2. If you remember, b1 is just equals to the initial voltage across the capacitor, initial condition, right? So b1 should be equals to v0, should be equals to 0. Okay, problem solved. Not entirely. We also have to find the value of the b2. So let me find this value on the next slide. Maybe slightly easier. Okay. Okay, stop worrying about this. I'm going to come back to this plot in a second. Let me find the value of the b2. Right, so if you remember, the other equation that we derived was minus alpha b1 plus omega d b2 should be equals to 1 over c v naught over r minus I naught. Right, so alpha is 200, beta 1 is b1 is 0, omega d is 979.8 times b, 1 over c is 2 nanofarads, v naught is 0 over r, minus I naught is minus 12.25 milliamps. Okay, so if you were to solve this, the value of the b2, sorry, okay, if you were to solve this, the value of the v2 is going to come out to be 100 volts. Okay, so the value of the v2 is 100 volts and the value of the b1 is 0 volts. So let me write down the equation now. I have to place everything over here in this equation. Okay, yeah. Sorry. Okay. V equals, again, the equation was b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt, right? So b1 is 0, so this is going to make the whole term 0, right? So we will be left with only b2, and b2 is 100. E raised to power minus alpha. What was the value of alpha? Alpha was 200 radians per second. E raised to power minus 200t times sine of omega d. Omega d was, what was omega d? 979.8. 979.8t. And this is false, and greater or equals to 0, v of t. Okay, so here's an expression for the voltage, and again, this is derived from just by solving those steps. And the second part asks to that you have to plot this thing for this time. If you were to plot this thing for this time, right, this is the response that you get. And there are some interesting things about this response, right? So for example, right, so this is an underdamped response. Underdamped response. A main characteristics of an underdamped response is it is oscillatory or a decaying oscillatory in nature, right? Or it has damped oscillations. It is going to have an oscillation. Oscillation means that it is going to move around to a certain final value, right? And then it's going to go down like something like this if you were to plot it all the way. So there's going to be an oscillation, there's going to be a damped oscillation. And then, of course, when what I just said, that the voltage V of t is going to approach its final value while it is alternating in between or across the final value. So it is going to go up and down the final value while being attenuated, which is going to be determined by the value alpha, and then it is going to reach the final value. Right, so swings about the final value decreases exponentially with time, and as you can see, right, so the swing, for example, the swing started from here, it reduces, it further reduces, it is going down. So swing across from the final values exponentially decrease because of e raised to r minus alpha t, or in this specific case, e raised to r minus 200t. So it is decreasing exponentially as it is as the oscillation is being exponentially decaying to reach a steady state, which is the final value over here. So here are a few other comments on, again, the characteristics of this oscillations. And this, again, this was our parallel RLC natural response in case of an underdamped response. So right, so this equation is valid for underdamped response, and here's an oscillatory behavior. So some of the comments that we already looked at, right? So the first one again is, as I mentioned, that the voltage over here, it oscillates between the positive and the negative, right, with in across the final values. And why is that? Because there are, again, two types of energy elements are there, inductor and a capacitor, right? So important thing is that energy and the capacitor are making it oscillatory, but not in every case. We looked at the overdamped response where the response was not oscillatory in nature, right? It was going all, for example, if for, in case of an underdamped response, right, it was going all the way like this. So that was not oscillatory while having still both energy elements. So energy elements in itself doesn't cause oscillatory nature. It is the value of omega naught and alpha, right? If omega naught becomes greater than alpha, this is what causes oscillatory nature or oscillatory response in the circuit. The rate of oscillation, right? So for example, how far it is going to go up and down and what's the rate of that is, that will be determined by the value of the omega naught, omega d. Right, so this is, so what is making this oscillation to decay? As we can see that the amplitude of this oscillation, right, this is getting smaller and smaller as it will reach to a steady state value. What is in the equation that is decaying it or reducing this oscillation? That is the value of this alpha. For a higher value of alpha, this is going to go down more quickly, reach to a steady state, less oscillations. Right, so again, the oscillation amplitude decreases exponentially by a factor of alpha. So alpha is also known as a damping factor, and omega d is called as a damped radiant frequency because of the word damped is coming due to the fact that in the underdamped response, this damping factor on the oscillation is coming from the alpha value. In case the alpha is 0, your oscillation is never going to stop, it's going to continue on. Oh, okay. In case there is no damping, you're going to have an alpha equals to 0. And your omega d will become omega naught, right? And your omega d become equals to omega naught. Because omega d, if you remember, was square root of, right? Because omega d was square root of omega naught square minus alpha square. So if alpha becomes 0, omega d becomes omega naught, and your oscillation is going to continue. So this means that whenever there is an energy dissipation element, which in our case is a resistor, because this is where the energy gets dissipated, which was initially stored in the inductor. No energy was stored in the capacitor, but in this case, it was stored in the inductor. So the initial energy that was stored in the inductor or any other energy storing element will get dissipated in the resistor, right, in a parallel RLC circuit. And if there is a resistor present in the circuit with some value, this means that alpha is not going to be zero, and this means that whatever the value of the alpha is going to decay the oscillation eventually. So there will be an eventual decay of the oscillation, and omega d will always gonna come out to be less than omega naught, and that is why this is called damped radiant frequency. Okay. So as the dissipated losses in the circuit decreases, the persistence of the oscillation. This is what the other comment that I mentioned, right? Depending on the value of the R, right? If the resistance is not present, let's say a resistance is open circuit, there's no element to dissipate the energy. This means that the oscillation will potentially continue. So for example, over here, we know that P power dissipated in a resistor, right? For example, equals to V squared over R. So if this value of the R approaches to infinity, this means that the power dissipation in the circuit will approach to zero. So in case of an open circuit, right, where the resistance becomes infinite, ideal situation, there is no energy dissipation in the circuit, and if there's no energy dissipation in the circuit, potentially your alpha value is going to come out to be zero, omega d will become omega naught, right? So alpha is going to come out to be zero, omega d is going to become omega naught, and your oscillation continues. Okay. Oh, okay, it's written over here. And the amplitude of the voltage does not decay, right? So for example, initially when the amplitude was decaying like this, right? So essentially it was going through some sort of an envelope, right? It was starting over here and then it was constantly decreasing. So this is not going to decrease, it is going to continue to go on. So for example, if in the previous example, if we were to replace R with infinity or an open circuit, then this is the equation that comes out to be. And if you notice that there is no e raised to power alpha term here. If there's no e raised to power alpha term, this means that there is no damping of the oscillation, and our voltage is 98 with the amplitude value, peak amplitude value, and we have a sine of 100t. Well, a sine of 1000t, right? So with that frequency of 1000, it is going to continue to oscillate at 1000 radians per second with an amplitude of 98 volts. Okay, so a good point to remember in this particular response, that it is an oscillatory response, and if there is a resistor present, there is a positive value of alpha, and there will be an exponent of e raised to power minus alpha t in the equation in the response, and that is going to decay the oscillation to its final value. I'm going to make one more point and then we are done. And this is when kind of I want to compare the underdamped response and the overdamped response in terms of circuit selection, right? We already looked at that in the underdamped response that we are talking about, we got this ringing or oscillation behavior, and in the overdamped response, there is no ringing, no oscillation, as we have looked in the past. So the idea is that, for example, how do you decide what, right? So what goes into the consideration of picking a response? Can you pick a response? And I would have loved to ask this question in person, but how can you pick a response, right? Again, the response, whether it is an underdamped or overdamped, or in the future we're going to talk about critically damped, it all comes down to the values of alpha and omega naught, how they are, if omega naught is greater than alpha or omega naught is less than alpha, or they are both equal, right? It picks a response. How do you pick the values of alpha and omega naught? Alpha is 1 over 2 RC, omega naught is 1 over square root of LC. So based on these resistance, capacitance, and inductance values, you can potentially pick up the values of alpha and omega naught, and you can make your circuit behave in a certain way, in an overdamped response, in an underdamped response, or in a critically damped response we're going to talk about. So let's look at both of them in a second. Let's talk about the underdamped response, where we have this oscillation, decaying oscillation of the response, right? The good thing about this response is it reaches to its steady state value quicker than an underdamped response. Than an overdamped response. It will reach to a final value quicker than overdamped response. This oscillatory behavior. So that's a good thing. The bad thing is that, of course, it is going to oscillate. You're going to have values going up and down the steady state values. Sometimes that may not be desired. But if you are okay with the point is that if you're okay with the oscillation and the amplitude of the oscillation, that is decided by the alpha as well. If you're okay with that, then you can get to the final steady state value faster in an underdamped response. However, if there is some sort of a requirement in a circuit that will prohibit you of reaching a particular voltage value, a voltage value exceeding a certain value, right? So, for example, the voltage should not exceed a certain final value. If there is some sort of a precondition built in there, then you don't want this oscillation behavior to occur, right? Because in the oscillatory behavior, you may have an oscillation at the starting end of it, where it can be greater than the final value, for example, or other some other particular voltage value, right? So in case of an overdamped response, the good thing about that is that it is not going to up and down the final value, and it is always going to go down and then reach to a. So for example, again, right, if you remember, I can draw it again here. This is, for example, how it looks like. It is, for example, if there's some initial voltage V naught, it is going to decay like this and then come down to a final value. So it is not going to go up and down, and it is not going to oscillate. The only that is a positive thing. It's not going to oscillate. Sometimes we don't want oscillations. The con is it is going to take more time to reach to a steady state as compared to an underdamped response. Okay, so this is what we have. Again, if you were to solve any circuit in terms of an underdamped response, and you are looking at the natural response of a circuit, all you need is this thing, right? You find the initial conditions, right? You determine the value of alpha and omega naught. You find out which response it is. In case of an underdamped response, this is the equation that you have for the response, right? That you don't need to redrive in terms of solving the circuit. You just need to fill in the variables. Omega d equation is this, and b1 b2 equation are this. So you can fill out all of these variables, you get a response. And then when we look at the response itself, it's a decaying oscillation. It's an oscillatory behavior which goes up and down the final value, but there's a decay of these amplitudes of this oscillation by a factor which kind of dictates by e raised to r minus alpha d the alpha value, right? And which depends on the resistance value. Okay, great. So this is what we have. In the next lecture, we're going to talk about critically damped response as well, and we're going to do a circuit example for that. All right, with that, thank you so much. Have a great rest of the day. Bye.